So before we get really started, I want to kind of present you with a situation that can help us work through this definition in kind of a real life scenario. So I'm going to show you a video, and in this video, you're going to watch a little girl who's going to go for a little run. So I'm going to play it probably twice so you can get a good look at it. It's just twice. But what you're going to look for is her speed, right? So her distance, how fast she's going. And just pay attention to it the first time, and then we'll talk about how we can use calculus to analyze what's happening. All right, so hopefully you can see that. I'm going to play it one more time. So this time what you want to focus on is how her speed is going to change, right? So hopefully you saw that she started out kind of slow, sped up a little bit, and then slowed back down. So here it is one more time. All right, so what I want us to do together, if you don't already have something, you might want to have some scrap paper on hand or a notebook so you can do a little bit of work with us. So here's a graph, right? I have distance as my y values and time as my x values. So I want us to draw a quick sketch of what her distance looked like over time. So I'm going to give you about 10 to 15 seconds to kind of come up with a rough sketch on your own. And hopefully you got something like this. Obviously, it's going to be a very rough sketch, right? Because we don't have a lot of data to work with. But notice how she kind of started out a little bit slow, sped up in the middle, and then slowed down a little bit on the edge. So her distance was increasing the whole time, but it increased slowly at first, and then faster, and then slowed down again, right? So now what we want to talk about here is what information that we can gain from this. So I like to run. Running is fun for me. So when I go for a run, after my run, I look at my watch and I get some data, right? Because not only do I like to run, but I really like math and I really like data. So I might want to see what my average speed was, right? So I know that I ran for however many miles for however much time, and I want to figure out what my average pace was. So to do that, I'm going to calculate where I started and then where I ended, right? And I'm going to find what we call the average rate of change. So before calculus, we've done this before. What do you think we could do to find the average rate of change between these 2 points? Perfect. Paula said slope, and she's absolutely right, right? We're going to find the slope of the line that connects those 2 points. That's called our average rate of change. We already know how to do that. We learned how to do that back in Algebra 1. So I'm going to shorthand here just to save a little bit of time. But if you remember from Algebra 1, right, our slope or our average rate of change is going to be that change in that y value over the change in the x value. In my problem, it's the change in distance, right, over the change in time. So that's going to give me my average rate of change, my average pace. So overall, how fast did I go? That was Algebra 1. We can do better now, right? We're in calculus. So another thing that I might want to talk about is, well, my average rate of change is good, but I want to know how fast I went at maybe a certain point, right? So let's say that I actually care about how fast I was going right here, okay? Because that's probably about the fastest that she was going, right? And I want to know, what's that speed? What's that rate of change? So I kind of have to work with this a little bit. Right now I have this average rate of change, right, between the starting and the stopping, but I want something that's a little bit more accurate. I want a slope that's going to be a better interpretation of what I got. So maybe I don't have to use that first point and that second point. What could I do to those 2 points to help me maybe get a better estimate of how fast I was going at that point? Hopefully you're thinking, move them close together, right? So instead of taking the first point and the last point, I might squish them together a little bit more, right? And get 2 points that are closer. Maybe I'll find a point that's when she started running fast and the point where she stopped running fast and connect those. If you look at that slope right there, right, that's probably closer to the speed that I was doing at that red point, hopefully, right? So in theory, we think, okay, well, if that's better, how could I get even better? What could I do? Get even closer. So now I got my green points. I'm connecting those. I got a point that's even 2 points that are even closer. Now my slope is going to be even better. But it's still not perfect. It's still just an estimate. So the theory is, could I take those 2 points and somehow get them closer and closer and closer and closer and closer and closer together until maybe they were really right on top of each other? And if I could do that, then I could find my speed at that very instant, right? That instantaneous rate of change. So we've been doing calculus now for about a month at least, if you're in the Northeast, more if you're other in the country. So what do we already know in calculus that helps us get closer and closer and closer and closer to a point, but maybe not exactly touch it? Here today, hopefully you're thinking limits, right? Limits, we know the limit, right? If I want to get closer to a value, I'm going to take the limit. So in this case, I want to take those 2 points, right? And I want to get the 2 points so that they're closer and closer and closer together. So what I'm really doing is I'm taking that change in x, right? That's here. And I'm taking that change of x and I'm making it negligible, right? I'm going to get it smaller and smaller and smaller so that it's no longer even a distance. So what I want to do is take the limit as delta x. And if I can do that, then I'm going to have what we call my instantaneous rate of change, right? The change, the slope at an instant, right? So I know exactly what that speed was right at that red point if I can somehow manage to take the limit as my delta x approaches 0. So that's the theory behind it, right? So let's clean that up with some notation and talk about how we can do it practically. So we call this the limit of the difference quotient, right? The difference quotient is our, basically our y2 minus y1 over x2 minus x1 that we learned back in Algebra 1. We're going to make it look a little bit more sophisticated, right, in calculus. So we're going to take our f of x at 2 different points, right, over our x at 2 different points. So one of the versions of the definition of the derivative looks like this. So let me talk about what all these parts mean. So first of all, right here is one of our notations for the derivative, okay? So we just talked all about how our goal is to find a slope between 2 points, but instead of it being 2 points, we're going to smush those 2 points together to get it only 1 point. That's what we call the derivative. So the derivative is our slope of a function at 1 point instead of at 2 points. So we kind of decided, well, we have this change in y, this delta y and this delta x, that represents 2 different points. So if we take those 2 points and we smush them together, right, we now have what we call dy and dx, right? That's the notation for derivative, or one of them. We'll see some other ones later on too. And so we're going to define our derivative as a limit, right? So the limit basically is going to be as we take 2 points and we smush them together. So here in a graph, I know it's kind of small, or at least it looks small on my screen. Let me see if I can make it a little bigger for you. Get rid of that. And oops. There we go. So what we're basically doing here is I've created 2 points, right? So one of my points here is on my screen. It's in a different place. So let me get rid of that. All right, so one of my points is a f of a, right? And another point is x f of x. So basically, I've just defined 2 points. One of them is define an a value, right? This point is actually looks like what, 6, 2, but it can be any point that I want it to be, right? And the other point is just another point, right? X, f of x. So we have two different points going on here. And what I want to do is I want to take that top point, that x, f of x, and I want to try to slide it. It's not working for me here. Here we go. Right, so I basically want to slide it. You guys can't see that. Well, the theory there is I take that purple point at the top. You guys can see that purple point, and you want to slide it down so that it becomes closer and closer and closer to that a, f of a, right, until they're right on top of each other. Let's see if that works. Oh, there we go. All right, so I'm taking that x, f of x, right? And right now I have what we call a secant line, right? So it's a line that connects the 2 points, and it's giving me an average rate of change, the slope between those 2 points. As I bring that purple point back together, right? Notice how that slope gets closer and closer to what now is going to be the tangent line, right? So can't make it actually go on top. So now I have a tangent line, right? So it's the slope of that curve right at that point right there. So that's what we want, right? We want to take those 2 points and we want to squish them together. Move that back out of the way. So that's where this definition comes from, right? So it's the limit as x approaches a. So our two x's are going to come together. I've defined one as a, the other one is x. As x approaches a, and then f of x minus f of a over x minus a. So this is one of our definitions of the limit of a difference quotient. And this is the one we're going to use when we care about a specific value. So if we want to find the derivative of a function at a certain point, this one can sometimes be a little easier. So let me show you what I mean by that. So here's an example. We're going to find the slope of the function f of x equals 1/3 x squared minus 4 at the point x equals 2. So I've drawn this picture in here, right? There's my parabola, 1/3 x squared minus 4. And I want to find the slope of that function at x equals 2. So basically what I want is that rate of change right there at that one point, the slope of the tangent line. So what we're going to do is we're going to use that limit definition that we just talked about. So the limit as x approaches a of f of x minus f of a, x minus a. And we're going to start plugging stuff in and see what happens, okay? So the limit as x approaches a, f of x is 1/3 x squared minus 4. And so f of a is actually going to be f of 2, right? And so I got to go back and fix that because x is not approaching a, x is approaching 2, because that's the value that we want there. So as x approaches 2, of 1/3 x squared minus 4, now minus whatever f of 2 is. So we can go ahead and plug in 2 to our function. You can probably also look at the graph if you could see it well, but we can do it the algebraic way here. And then on the bottom, we have x minus, and our a is 2. So let's clean that up a little. So here we have, let's see, 2 squared is 4. So we have minus 4/3 plus 4. Okay, so hopefully you notice that we have some things canceling here, so we can get rid of those. We have 1/3 x squared minus 4/3 all over x minus 2. So now at this point, hopefully you'd be saying, okay, it's a limit, so I should try to plug in 2, right? See what happens. So we're going to plug in 2. we're going to think about that. X2 squared is 4, so we get 4/3 for that first part. Minus 4/3, that's 0 on the top. Plug in 0 to x minus 2 on the bottom, you get 0 again. Hopefully, you've gotten to the point in limits now in your classes that you're saying, I know what 0 over 0 means. It means do more work. I'm not done. That's not conclusive. So I got to find something that's going to make me able to keep going. Okay? So we are going to look at that and see what we can do to cancel or reduce or kind of figure something out. So I'm going to play with this a little bit. I'm going to, if you're anything like my students, you see fractions inside of fractions, you get a little panicky, right? So let's kind of try to take care of that. I'm going to take that 1/3 and I'm going to factor it out. So it's kind of hanging out front a little bit. And then hopefully by doing that, you're starting to look at that and say, oh, I got it, right? I need to make that bottom go away, and I've got something there that's pretty obvious. So what do you think? What are we going to do with that numerator to help us reduce this fraction a little bit? Factor is correct. Good job. So we're going to factor that top. Difference of 2 squares. And so then we have the awesomeness that is reducing, right? So we've got 1/3 x minus 2, x plus 2. The x minus 2's cancel, which now gives us the limit as x approaches 2. Of 1/3 x plus 2. So now we can actually go ahead and plug in that limit, right? We can plug in the 2, and we get 1/3 times 4 equals 4/3. So what we found here, right, is that we have found the slope of this curve at that very point. So let's go back up and look at this graph here. I'm looking at x equals 2. And I can see that there is a tangent line right there, right? That represents the slope of the curve at that point. And the slope of that line should be 4/3, right? That's what we just found. We found that we took the average rate of change, we smushed it together by taking the limit, right? And so we found an instantaneous rate of change, the slope of that curve at that very point. So when x is 2, the slope of the curve is going to be 4/3. So someone asked a question about the notation, right? So let me go back to that real quick. So the difference between dy over dx, right? And then you have said that you've seen like just d over dx. D over dx is really the same thing, okay? But usually you're going to then see a function right there, right? So you're taking the derivative of f of x, right? But it really means the same thing, just like y and f of x are kind of interchangeable, except for that f of x is a little more specific because it tells us it's a function. It's the same case here, right? dy over dx is the same as d over dx, but if you use just the d with no y on top, then you have to kind of have an input, right? You have to have a function that you're taking the derivative of. So that's sort of the difference between those. They're really the same, but they're just a different way of looking at it. We're going to look at other notations too as we go through this presentation. So for example, here we are, new notation. So the definition that I gave first is one that's probably slightly less commonly used, but we want you to see it because it works really well if you're looking for the derivative at a specific point. But a lot of times we're just looking for the derivative in general, right? We want to know what the slope is at all of the points, right? Not just one place. So we need a more generic definition that's going to help us find the derivative at any point along the curve. So this is what that is. Notice I'm introducing a new notation here, right? So this is read f prime of x, right? So f prime of x is just another way of saying the derivative of the function f of x, right? So it means the same thing as dy over dx. It means the same thing as d over dx of f of x. They're all kind of saying the same thing, but different notations. Excuse me. So another way to write it is f prime of x. I just wanted to show you that. So now here's a new definition of derivative. I say new, it's actually the exact same one, just written a little bit differently. So somebody just asked, is the one we just used for tangent lines and this one for secant lines? And so no, they're both for tangent lines. I'll talk about that a little bit more as we go through this. So this one here is basically used, it's the same thing, right? It's just a different notation. So here's how I'm going to explain it. So if you look at this picture here, I just picked 2 points like I did last time, right? But I'm going to call them something different. So this black point right here is x f of x. And then I have a second point. And I'm going to define that second point as a certain number of units away from the first point. So instead of them just being arbitrary, I'm going to say I have 1 point and the second one is h units away. So you can kind of see that in the picture right there, right? So the distance between my 2 points is h, which means my first point has an x value of x. My second point is going to have an x value of x plus h because they're h units apart. My y values are going to follow, right? So my f of x, and then I have f of x plus h, whatever x plus h is. And so the idea is still the same, right? We start with a secant line, 2 points, and then we're going to take that second point, that x plus h, f of x plus h, and we're going to slowly bring it down towards the x f of x. So we're going to move that red dot, and we're going to move it down, down, down until it's on top of the first one. So what does that actually do? It actually takes that h value, right? And it makes the h value shrink. So the distance between the 2 points starts out far apart, and it moves closer and closer and closer and closer together until h is going to be 0. So that's where this definition comes from, right? The limit as h approaches 0. The distance between those 2 points was called h, and we're going to make it become 0. The equation is still the same, right? This is still y2, and this is still y1 from the regular old slope formula, right? F of x plus h minus f of x. The bottom actually comes from the change in x. It doesn't look like it, right? But you have x plus h is your first point, and then minus x is your second point. Your 2x's cancel, right? So you're just left with that h right there. So this is just another version of the same definition. They both come from the same concept, the same idea. The notation is just different. The way you would answer the way you would use the two, the first one we learned, you use that when you're finding the derivative at a specific point. So I said, hey, find that derivative when x equals 5. Then you can use that one. It's a little bit easier to work with because there's more numbers, less variables. This one you're going to use when you want a more generic answer. So this one is going to result in an equation as an answer rather than a number. So you're going to see that happen in a second. So this is actually the more commonly used one. So we're going to play with this one a little bit. So find, oh, that's not English, but find f of x, f prime of x for any given point. So see the difference? In the last one I said find it at x equals 2. For this one I'm saying find the derivative at any given point on f of x equals 1 over x plus 3. So I want to find my function of the derivative, but I want to find it for any point that's on that curve. So we're going to start by looking at our formula. And starting to plug things in. All right, so let's look at our function. So if I want f of x plus h, what I really want here is to take my function and plug in x plus h. F of x is just 1 over x plus 3. And I'm going to put that all over h. So initially what you would hope to do is plug in 0, right? And if you plugged in 0 for h, you would find that you get 0 over 0, which means do more work. So we got to keep going. We have to do something to this fraction to make it work. So we're going to use algebra, right? So I've got fractions. Again, if you're one of my students, the fractions inside of fraction thing is something you never want. So Emmeline, you're absolutely right. We're going to find a common denominator, right? We're going to try to squish these fractions together so that we can hopefully simplify something out. So our common denominator here is basically just 1 times the other, right? Because there's nothing really in common factor-wise. So I'm going to multiply this one by x plus h plus 3. And the other one times x plus 3. And so let's see what happens there. So that's the numerator. If you want to get rid of that fraction inside of a fraction thing, we can kind of make h chill right there, right? Because that's the same as dividing by h is multiplying by 1 over h, right? So I can do a quick 1 over h multiplication there. So I could have factored out the denominator too. Generally speaking, in most of these circumstances, you're going to want to factor things so that you can cancel things. So I wouldn't recommend multiplying things out unless you're stuck and there's nothing else to do, right? Because then we'll multiply them out and see what happens. But the denominator, we're going to leave the way it is for now, unless we have to change it later. But we can look at that numerator a little bit and clean that up. And awesomely, we can see that we've got some things that are going to cancel, the x and the negative x, the 3 and the negative 3. Gotta put the rest of my denominator in here. So let's see what's left. I have a negative h on the top. I have an h on the bottom, and then an x plus h plus 3 and an x plus 3. So now we also have an h that cancels with the h on the bottom, right? Since the only thing that's left on the top is h. And I can write that actually out just so that we don't confuse anybody. We have an h on the top. Sorry, negative h on the top. An h on the bottom. And so those h's are going to cancel. So now we're ready to plug in the h equals 0. So when we plug in h equals 0 right here, that's the only h we got left, that goes away. So we have negative 1 on the top. On the bottom, we have x plus 3 times x plus 3, which is x plus 3 squared. So let's talk about what that means, okay? So we did a whole lot of work, right? And I always find sometimes with calculus, right, we get so excited, we do all this algebra and it's wonderful and we get an answer, and then we're like, all right, well, what did we just do? What did we just find, right? So let's go back to what we talked about. The whole purpose of this definition, right, is we're finding the derivative. The derivative is what happens when we take this average rate of change, that slope between 2 points, and we make it a slope at a single point, right? So we now have the slope of any point on that graph. So here's the graph of that function, right? And so we just found that the derivative is that. So basically what that means is I can pick any point on this graph, and I know what the slope of that graph, the slope of that function is at that point, right? I could make a tangent line, and I would know what that slope would be, which is really cool, right? I can find the slope now of any point on that curve. For years, literally, Algebra 1, geometry, Algebra 2, pre-calculus, we're finding slopes of lines. That's it. That's all we could do. We might sort of talk about the slope of a quadratic maybe in there somewhere, but really all we've ever been talking about is slopes of lines, because that's the best we could do. We now have this one tool that can give us the slope of any curve at any point just by using that limit definition, by taking that average rate of change and turning it into that instantaneous rate of change. So that's super powerful. So what can we use that for, right? We can use it to do all kinds of things. So let's practice one more. So I want to find the derivative of f of x equals the square root of 2x plus 7 for any given point. Okay, so I'm going to start out by finding it just in general. So I'm actually going to pause here for a minute, and I'm going to let you guys kind of see how far you can get on your own, okay? So I'm just going to give you like 90 seconds or so, and why don't you do this on paper and see if you can get yourself through finding the limit definition of a derivative. I'll give you a little hint if you get stuck, right? We have square roots. So in order to kind of get rid of a square root, we multiply by the conjugate. So that's your little hint if you get stuck. But go ahead and see what you can do. All right, so how are we doing? Hopefully we got somewhere. If not, that's okay too. We'll practice a little bit more, right? So I've set mine up, right? So the limit as h approaches 0, taking the square root of 2 times x plus h plus 7 minus square root of 2x plus 7 all over h. And now I have to try to algebraically make that better. So if I plugged in h equals 0 right now, I would get 0 over 0. So I got to keep going. I gave you the little hint that you're going to want to multiply by the conjugate, right, to get those square roots to at least go away in the numerator. They're going to come out now in the denominator, but we'll deal with that as it comes. So I'm going to multiply by conjugate here. So on the top, I'll get 2x plus h plus 7 minus 2x plus 7. Again, I'm not really going to distribute the h in the bottom because I'm hoping that that h is going to go away, right? The ultimate goal is to try to get rid of it so we don't have a 0 on the bottom anymore. So let's clean up and see what happens in the numerator a little bit. right, so hopefully, again, you can see you've got some magic happening in that numerator, right? So the 2x and the negative 2x are going to cancel. The positive 7, the negative 7 are going to cancel. And so in the numerator, we're just left with 2h. And then that big old mess in the bottom. And the magic that we wanted to happen does happen, right? So we have that h in the top and that h in the bottom that cancel out. That gets rid of our 0 over 0 problem that we had. So now we can try plugging in h equals 0 again to see what happens. We plug in h equals 0, and we get 2 on the top. On the bottom, hopefully you notice that if I take this h away, my two square roots are the same, right? So they're both going to be square root of 2x plus 7. So I'm actually going to have 2 square roots of 2x plus 7. And then those 2's cancel. And we get 1 over root 2x plus 7. So that, again, what did we do? All that work. Our goal was to find the derivative. Sorry, I don't know why it's doing that. But find the derivative of f of x equals root 2x plus 7 for any given point. So we just found that, right? We found out that f prime of x is going to equal 1 over root 2x plus 7 for any given point on that curve. So the nice thing about this versus the first example we did is, since I know it works for any point, I now can go ahead and ask you questions about a specific point. So if I want to know what the slope of the curve is at x equals 2, you could tell me that, right? You could plug 2 in for x, you could find it out and give me that information. So that's what we're going to do here. And it's a perfect example of a question that the AP test asks all the time, is using f prime of x to find something useful. So I want to use the slope of f of x that we just found to find the equation of the tangent line when x equals 2. So remember what we're doing, okay? We have a curve, f of x equals root 2x plus 7. I want to know what, if I drew a tangent line there, right? I drew a line that has the same slope as the curve, so it touches it, and it's a tangent line. What would the equation of that line be? So I'm going to go ahead and I'm going to use what I just did to write that, okay? So how do we write an equation of a line? We have some options, right? We have slope-intercept form, we have point-slope form. Probably the more useful one here would be the point-slope form, because whether you realize it or not, we don't really have the y-intercept. We do have a point, and we actually have the slope. So we're going to start with point-slope form. You're probably most comfortable with it looking like this. And we're going to stick with that, but I'm going to kind of show you how we can change our notation to make this fit our situation a little bit better and work for us. So we're still going to use the same formula, but our point now is going to be, instead of x1, y1, we're going to call it x f of x. And instead of m, right, we now know that our slope is actually f prime of x. So we can change our formula a little bit to look like this. Actually, let me change that to not x. That's going to be confusing. I don't want to confuse anybody. We'll make a point A. Otherwise, I'd have x minus x, and that would just confuse things, right? So we'll pick a point randomly A, f of A, and then our slope will be f prime of x, okay? So now we can plug in y minus f of A equals f prime of A. Let me fix that one too. X minus A. So this is cool because we actually have all of this information. We just didn't really know it. So A, in this case, it says use the slope of f of x equals square root of 2x plus 7 to find the equation of the tangent line when x equals 2. So our A is going to be 2. So we can find f of 2, right, by just plugging it into the function. And we can find f prime of 2 because we already know what f prime of x is. We just found that on the last slide. You can rationalize that if you want. You don't have to, depending on the circumstance. If it was a multiple choice question, they might rationalize. If it was a free response question, you certainly don't have to. It's just kind of an extra step. So then we can go ahead and plug it back into the formula. Now we get y minus root 11 equals 1 over root 11 times x minus 2. Which is the equation of the line tangent to the curve f of x equals root 2x plus 7 at the point x equals 2. Okay, so that's kind of a sentence that you should start getting comfortable with. As time goes on, you want to be able to interpret a derivative that way. So when I find a derivative and I make an equation, as soon as I say derivative, you should be thinking slope of the tangent line, right? Or slope of that function at a given point. And if I asked you to find the equation of the tangent line, then you certainly can. And that would be the slope, that would be the equation of the tangent line at the point x equals 2. So I thought I'd throw kind of a tricky one in here for you, okay? This is one that they probably wouldn't expect you to come up with on the AP test because it's a lot more of a test of your trig than it is a test of your calculus. But I thought we would do it just for fun as a little trig refresher here. So I want to find f prime of x if f of x equals sine x, right? And then if we can do that, I think we'll have enough time. We can then use our answer to find f prime of 2 pi over 3. And then we'll also talk about what that means, okay? So we're going to start by filling out our limit definition. And hopefully, most people are going to get to this point and be like, okay, well, now what, right? So plug in 0, you get 0 over 0. Not a whole lot of algebra we can do here. So what you don't want to do is try to distribute that sign, right? Sine is a function. It's an action. It's not a number. So you can't just multiply it in. So we kind of are stuck in that algebra regards. So when we get stuck in algebra regards, I always tell my kids, well, what do we know other than algebra? And usually the answer is trig. So you kind of have to go back and think about your trig identities. So again, I don't see this as a problem that would necessarily pop up on an AP test because, you know, they're not really testing your trig identities. But it is something that's kind of cool to see. So you have to know the trig identity for sine of x plus h, okay? And so that turns out to be, write it here, sine of x cosine of h plus cosine of x sine of h. So hopefully you're like, oh yeah, I remember pre-calc and we did something. We have a teacher at our school that actually makes the kids dance and has a little dance to go with this. So maybe someday I can show you that. So that's the trig identity that's going to help us there. So then we have the minus sine x over h. And you might be like, that was awesome, but I still have no idea where to go from there, right? So I still don't have a lot of algebra going on here. And I have more trig, but still it doesn't seem super helpful. So we are going to do a little bit of algebra here, and hopefully the only thing that you look at that you could possibly algebra with is getting those sine x's together. So that's what I'm going to do. And then I'm going to go ahead and factor out that sine x. I'm also, just to kind of save some time and steps here, I'm going to actually break the fraction into two. Okay, so it's all over h, but certainly I understand fractions well enough to know that I can split a fraction, right, with a common denominator. And I'm doing this for a reason. I'm doing this because these now have limits that hopefully at some point during your first month or so of school, your teacher kind of showed you and taught you about as ones that are going to come up frequently that you kind of have to know, particularly this one right here. Okay, the limit as, usually it's x, but whatever, limit as h approaches 0, sine h over h is a limit that we have to kind of know. So you probably learned it, you might have learned it with the squeeze theorem, right? This is an example that's frequently brought up with the squeeze theorem. But I can quickly show you what it looks like. So it looks something like this, right? There's actually a hole at the point, at that maximum right there. So that hole is because, right, if you plugged in 0 to sine x over x, you get 0 over 0, which is undefined, right? We can definitely, so Yao said we can use the squeeze theorem, sandwich theorem, absolutely. That's probably the way you learned it. I'm not going to take a lot of time to go through that right now because that's a more complicated thing and that's not what the objective here is, but that is probably where you learned it and absolutely is a great application. But you can kind of see by the graph what the limit would be in this case, and the limit is supposed to be 1, right? So that is something that you should learn with the squeeze theorem, and you probably did. But that limit right there is going to turn into 1. This one is less commonly taught, but is another one that's kind of frequent and also in the same category as the sine x over x. It's usually written the other way, though, so 1 minus cosine h over h. Just get Desmos up there. So you can see that one is going to have a limit of 0, right? So this is written backwards from that, but you could certainly switch it around, right? You could make it 1 minus cosine h with a negative out front, so let's do that. So now, and when we plug in, right, this here is going to go to 0. This here is going to go to 1. So we end up with, negative sine x times 0, which is just 0, plus cosine x times 1, which is just cosine x. And that is our derivative. So we just proved the derivative of sine x is cosine x. We can then use it to find f prime of 2 pi over 3, right? So f prime of 2 pi over 3 would be cosine of 2 pi over 3. All right. 2 pi over 3 is a triangle in the second quadrant, right? Across from the root 3. Across from the angle is the root 3. 1, 2. The 1 is negative because it's an adjacent side. So you get cosine is negative 1/2. So the interpretation, f prime of 2 pi over 3 is the slope of the function sine x at 2 pi over 3 is actually going to equal negative 1/2.